Hi, welcome to AP Physics C Unit 6 for mechanics. This is the last video in this unit. Remember, this is simple harmonic motion. And so what we're going to look at is the pendulum and really look at the three types, but then we're only going to derive the expression a period for one of them, which is going to be our simple pendulum. So in Physics C, there's going to be a potential three types of pendulums that you're going to see. One that you saw last year, or if you've taken a Physics 1 course, which is what we call the simple pendulum, and it's just going to be a mass or a bob attached to a string that is allowed to swing freely. That's our basic pendulum. But what we're going to do here in Physics C to bring calculus, we're going to include the physical pendulum, which is a rigid body that undergoes fixed axis rotation about a fixed point. So that would be like if I were to take a baseball bat and turn it into a pendulum, right? But one thing you can see in the picture is it's all kind of centered around that center of mass idea. And then a torsional pendulum is essentially a disc that's allowed to spin right on a string. So sometimes when you hold up a disc and you start to see it spin, that's due to the torsional aspect of this. But those are the three types of pendulums that we're going to see. And what we're actually going to do in our example problem is we're going to derive the expression for the simple pendulum, the period of a simple pendulum. All right, so here in this question, derive an expression for the period of a simple pendulum of mass m hanging from string L, string of length L. The pendulum is pulled back with an angle less than 15 degrees. Now, the less than 15 degrees is going to help us because it's going to allow us to look at what we call a small angle approximation. Right, so it's going to allow us to do a little bit of trig and to get rid of some of the trig stuff. And so one thing to note is that with a pendulum, that's the restoring force is this negative mg sine theta. And so that's what we're going to really look at when we do our F equals ma. And the other thing to note is that, right, it's going to move a distance, right, a vertical distance of, we'll call it, sorry, where's that? We're going to say that theta is going to be the ratio of what we'll call x over L. Sorry, I'm looking at my notes and I'm trying to determine. I've got so much stuff written down on them, right? No, that is a capital L. Okay, so the only force acting again will be that negative mg sine theta. That is our restoring force for the pendulum. And then that's going to equal ma. But remember, if you remember from the last video, and that the conditions of simple harmonic motion tells me the acceleration is equal to negative omega squared. Okay. And it's going to travel that short distance, and that's why we're just going to call that x. Okay, so it's along this line here. And if I were to make the triangle, this is the distance that it actually travels, right, in a way. So you can see things cancel out, the sine, so I get g sine theta equals omega squared x. Now, this is where the small angle approximation is going to help us. What the small angle approximation says, that the sine of the angle in radians is essentially equal to the angle itself, right? Now, remember, this is all in radian measure. So like pi over 2, this would be less than what, pi over 6 or pi over 8 or something like that, whatever gives you 15. And so what that allows me to do is say, instead of saying g sine theta, I can just call it g theta. Okay. Well, the other thing that happens is you would actually plug in, right, this ratio right here, right? Well, that's sine theta, right, equals x over L. So it's the same thing, right? It's going to work out to be, what I need to do is substitute in some relationship for theta or sine theta, relating my x distance, my length of x, and the length of the pendulum. And so now I can say that this is going to be gx over L equals omega squared x. And just like we did with the other, in the other video with the mass spring, we need to find omega. So what happens is this x cancels that x. There's my omega squared. So that tells me that omega is the square root of g over L. But then I plug that into the omega equation, solve for period. And just like I did before, I can now simply reverse or invert my fraction. So there is my simple pendulum, right? So even if you don't use a small angle approximation and do it for any angle, you're still going to substitute in that ratio of x over L. And so that's why with pendulums, though, they're only really effective up until 15 degrees or so. Once you get out past 15 degrees, then there's more of an effect of some of the other forces acting on it, then that causes not to be nice swinging pendulum motion. Now, you could do the same exact stuff, right? The same exact information or process for the other two, which I'll provide links in the description to take you to those. All right, so that is the end of Unit 6. So when it comes to mechanics, there's only one unit left to do, and that's gravitation. And that's going to be another short unit because, again, that's only Unit 6 and Unit 7 are a small portion of the exam, where most of the focus is going to be on 1 through 5.